So first of all, I would like to thank the organizing committee for the invitation to present our paper as a theme lecture. I'm honored to present on behalf of my co-authors who are listed here. My name is Serena, and I'm a senior geotechnical engineer at the Geotechnical Consulting Group. And today I'll be taking you through how we can optimize back analysis of offshore pile driving in wick rocks with a data-driven approach. As offshore wind continues to expand to meet the net zero targets, increasing number of pile foundations are being installed through wick rocks. However, assessing the drivability of such piles in these formations remains a challenge, as we've just listened to Elizabeth's keynote lecture. Current guidance is limited, and the uncertainty associated with hammer selection and the need to avoid pile runs or refusals often leads to significant cost. But with every challenge comes opportunities. As engineers, we leverage various tools to reduce such uncertainties, particularly in improving our site-specific soil resistance to driving predictions. And in this presentation, I will focus on how we can leverage historical data for offshore pile installation in chalk. So chalk occurs as a wick-likely cemented limestone that underlie many offshore wind farm development areas in Northern Europe. The Alpaca and Alpaca Plus joint industry projects led to a CPT-based method for predicting the chalk resistance to driving. And this methodology was developed based on signal matching analysis of dynamic field test. While signal matching analysis offers very valuable insights, it is often only possible to consider a few blows recorded as selected depths on a small subset of instrumented piles. On the other hand, it is common to have blow count and hammer energy records for many more piles over the full penetration depths. And ideally, we would also like to back-analyze this to inform the SRD predictions. But it's important to note that such back-analysis is not a straightforward process. It must address very highly nonlinear problems whose results are influenced by numerous factors. And this presentation aims to set out a consistent and systematic framework for the back analysis for utilizing blow count records to assess and enhance the performance of existing SRD methods for chalk. And I would illustrate this using example SI and pile driving data for the German Baltic Wikinger offshore wind farm, where trial and production piles were driven through glacial and fluvioglacial tills and chalk. At the Wikinger site, there are 70 jacket structures with CPTs available. Each jacket was supported by 4-pin piles driven using a Mank hammer. And now this simplified flowchart shows the framework proposed for the back analysis. The detailed steps are blanked at this moment, but I will take you through the following slides as the details will be reviewed. So first, input data. We need information on the pile and hammer characteristic, the driving data, and also CPTs. Filtering, cleaning, and preprocessing the input data is a crucial step, although often overlooked, and I would illustrate this using data from Wikinger. So prior to performing any preprocessing, it is useful to set out a set of filtering criteria to identify suitable data sets. And for Wikinger, we have applied these criteria to ensure we have sufficiently meaningful data points within the chalk for the back analysis. And 25 of the 70 locations met this criteria. So you can see, actually undertaking this step helps reduce the time spent on preprocessing irrelevant data. And for each of the selected locations, we then have to undertake the relevant cleaning for the raw CPT data, for example, removing the artificial minima associated with the start of downhole CPT pushes and the maxima associated with thin flint bands. And when it comes to averaging, there are various approaches which are available from literature, but it is also very important to consider the form of the CPT traces that we're looking at and also the intervals of the blow count records that we're back analyzing. So for example, at Wikinger, the blow counts were recorded over 1 meter interval, so making any finer treatment of the CPT profiles inappropriate. And also considering the local variation of the CPT traces, we've decided to average the profiles over 1 meter depth windows. And before we can start any analysis, we also have to select an appropriate methodology for calculating the soil resistance to driving. And while the chalk forms the focus of this presentation, the pile driving behavior is in fact heavily influenced by the till, which overlie the chalk in most of the selected locations. And the Almen-Amrey formulation was used, and for the chalk, the updated SLD formulation from Jardine et al. Was used. And as far as the back analysis is concerned, the fitting parameters in red are the parameters to be optimized. So now with the input ready, we can start with the optimization for the glacial till. A key procedure in the back analysis involves deriving the expected SLD from the driving data. And we could achieve this using the so-called bearing graphs from a WIP analysis software. And this figure here shows an example bearing graph. But it's important to note that each graph is unique to a specific set of conditions as outlined in this mind map here. And using this graph, we can derive the expected SLD from the recorded blow count. But as I said, each of these components in this mind map shown here carry their own uncertainty. And therefore, the solution of the back-analyzed SLD is not unique, but for example, it varies, for example, depending on the soil resistance model adopted and the dynamic variables. So now on to the next step. So the objective of this back analysis is to develop an optimized set of SLD parameters from the driving data. But this optimization process requires a scoring measure to determine the fitness between the SLD back analyzed from the driving data and the SLD predicted using the existing formulation. And to do so, a scoring system adapted from the concept of normalized root mean square deviation, or NRMSD, proposed by Pericleos was used. This NRMSD, however, was formulated to assess the prediction of a single pile. So we have to modify this scoring system to enable the SLD parameters to be calibrated across all the piles that we're looking at. And to do so, we propose this joint optimization score, which is essentially an equally weighted sum of the NRMSD from all piles. But at this point, I would also like to highlight a potential caveat regarding the use of NRMSD, that it could potentially introduce a depth bias depending on the shape of the SLD profile that we are looking at and also the associated error distribution. So now with the scoring system ready, we would need an optimization algorithm. And in this study, genetic algorithm, or GA, was used to optimize the SLD parameters with the objective function of minimizing the sum of NRMSD from all piles. I won't go through the details of the genetic algorithm here, but more information can be found in the full paper. And I think a key, but currently not shown, step in this algorithm flowchart is, in fact, applying engineering judgment before the start of the optimization process. And defining sensible bounds to restrict the SLD parameter search space is crucial to ensure meaningful results, and it also helps to reduce the computational effort. So now with the optimized Almen-Amrey SLD parameters for the till, we can move on for the optimization of the chalk. And similar steps will follow, as you can see from this flow chart here. And just to demonstrate this concept in this presentation, although by no means statistically significant, 2 illustrative piles from the Wikinger database are considered. These 2 piles were back-analyzed using the workflow as discussed earlier, and the optimized parameters are shown in this table. The figure on the right compares the SLD back-analyzed from the driving records versus the post-predictions after the joint optimization of the 2 piles. So one thing that is important to note is that actually the back-analyzed SLD values are dependent on the shaft to end bearing ratio. So checks were made to ensure that the fitted parameters actually led to comparable ratios to those initially assumed. While this demonstration in this presentation only considered 2 piles, the full Wikinger dataset is being back-analyzed, established more statistically meaningful results. And in the future, other chalk offshore wind farm sites will be included in an expanded database, and the probabilistic approach can then be used to better quantify those uncertainties that I discussed earlier. So in conclusion, we presented a systematic, consistent, and data-driven workflow for back-analyzing the historical driving databases in WICROX, focusing on chalk, to improve the SLD predictions. While this approach appears promising, as you can see, great care is required to optimize this highly intricate process. And while most attention is often paid to the optimized set of SLD parameters, We would argue that it's equally, if not more, important to appreciate the decisions and assumptions made throughout the back analysis process. So that's the end of the presentation. Thank you very much for your attention.